I need to give another introduction.
Go for it.
All right. Hi, everybody. I'm Kalika Curry. I am a experienced IT professional. I've spent mostly about 8 years of my life doing IT, working in data in some way, shape, or form. Today, we are doing a book club discussion on hands-on machine learning with Scikit-Learn, Keras, and TensorFlow. This is the second half of chapter 9, which is the unsupervised learning models. We are discussing, what's it called? Gaussian Mixture Models. And if you give me just a moment, I will share my screen and run that up here. Can I get that to work? There we go. I think F5 is the button to play it. There we go. We're just going to scroll by really quick. All right, so Gaussian mixture modeling. This is what we are discussing today. Boom. Our first question is, what is Gaussian mixture modeling? So first and foremost, he mentions that it's some kind of Gaussian thing, and I completely forgot what Gaussian means. If anybody wants to head this up with me, I know we're talking normal distribution, but then he calls it a Gaussian, like it's a type Gaussian, but any kind of distribution. So what does that mean? Because from what my understanding of Gaussian, it's normalized, right? It's that bell curve shape that we're used to.
So
yeah.
Kalika, in the book, I had to go look at it too, and it referenced some diagram further up in the chapter, which showed a dots, speckled dots, but in a certain like ellipse formation, and then somewhere else it was like a more circular formation. So they may be normal distributions, but they have different shapes to them. So the mixed would be the different shapes of the pattern.
Yeah,
Okay.
that's right. So if you think of a normal bell curve, okay, if you took a bell curve and you kind of spun it around, the mode, the peak of the bell, okay, then you could have a two-dimensional Gaussian distribution in X and Y, and it would just look like this three-dimensional bell, so to speak, right? But if you did that where you spun it around, that would mean that the standard deviation in the X direction and the Y direction were the same. It would also mean that the X and the Y coordinates would be independent. So in fact, you can actually get one where, imagine it's a bell, but it's like stretched. It's longer in the Y direction than in the X direction. It's not a round bell, but it's an elongated bell, right? So that would be if the Y dimension had a larger standard deviation than the X. They also can be partially correlated, in which case, instead of it just being elongated, say vertically, it could actually be diagonal on an angle. And you can describe those relationships of what is the standard deviation or variance for each variable, and what is the sort of variance between the variables with the covariance matrix. So you'll see reference to capital sigma as the covariance matrix. But ultimately what it means is that you can just have different kinds of standard deviation, and they can be either correlated or independent, or partially, different levels of correlation. And so I can't really necessarily visualize it, give people an intuition beyond 2 dimensions. But if you're doing a high dimensional model, if you're doing a 12-dimensional model, then you have a separate mean and standard deviation for each of those 12 different dimensions. And then they could be independent, or they could actually be have various levels of dependency, which means that the shape of the distribution, the high density part of it, it doesn't need to be circular or spherical. It can be ellipsoidal, and the ellipse can be pointed in any direction. Does that make sense?
That totally drops the intuition on that, doesn't it? So my feel for that is to just try it. Like that's all I can get out of that. I can't really imagine looking at it and being, okay, this looks like this looks like a good Gaussian mixture opportunity. Yeah. So, but it does kind of make some sense, especially knowing what some of the hyperparameters are, which we're not into yet. But yeah, thank you for pulling that one out. So we know that Gaussian mixture models are using soft clustering, which we discussed last time in the last discussion around just clustering. And understanding that soft clustering means that rather than doing these, sort of this cluster belongs to cluster one, we have this sort of idea that there's a probability that it belongs to cluster one or cluster two or cluster three or however many clusters you have. So we expect that they will be ellipsoidal in shape, which is opposed to the dense clusters that we see within k-means. And similar to k-means algorithm, we have this sort of expectation maximization algorithm, and that's where these soft clusters come from. And then we find out that also, like k-means, we are in trouble of getting this sort of poor conversions. So you'll have to go through several iterations in order to identify the best solution. And this behavior is achieved through the changing of the n init parameter, whose default is 1. So you kind of want to check in on that one. Anybody want to have anything else they want to add to that regarding the n init parameter or anything up to this point? You just kind of want to jump in.
So Kalika, I don't know. I don't remember if you have more discussion on your next slide, but since this isn't that large a half chapter, right? We split it in two. It would have been kind of a long single chapter, but we split it. So I thought maybe we would want to talk a little bit about expectation maximization. And so I don't know if someone here could help just kind of give a high level overview of in the book, he doesn't really, I mean, he obviously can't explain all the workings behind all the algorithms, but I feel like that one paragraph didn't try too hard to explain expectation maximization, but EM is a pretty fundamental algorithm in machine learning. So I know didn't necessarily have a chance to prepare, but is anybody willing to kind of take a shot at that?
I'm running through my slides really quick to see if I have anything up there on that, and I did not, unfortunately, go into too much detail on the expectation maximization algorithm.
Okay, so I will try and do a poor man's job talking about likelihood and expectation maximization. So let's start with a simpler understanding of the problem. Let's say you had a single bell curve, okay, and you knew its parameters. So you knew it had a mean of 10 and it had a standard deviation of 1, okay? If I said to you, I sampled a data point and it was 11, how likely is it that this 11 came from this distribution with a mean of 10 and a standard deviation of 1? Okay, and so if you know the math around normal bell curves, you could say, oh, it's 1 standard deviation from the mean, and what is it, 65 something % of points fall within that or something like that. So you can sort of say there's a certain likelihood that it would fall in that distribution. But if I sampled and I got a point that was very different, I got a point that was 20, and it's 10 standard deviations away from the mean, you would say that it is got a very, very, very low likelihood, some very small number, to have come from that distribution. Okay, so most of the time when you think about us building models, we're building this model and we're making predictions. We're saying, what's the probability for this new unseen data point that it's class 1 or class 2 or whatever. So in expectation maximization, what we're doing is we're doing the opposite thing here. So when you do model inference, you've built your model, so now you have all your model parameters. Okay, you figured out what all the weights are and whatnot. And now you're making a prediction, you're getting a probability. So dogs versus cats, you're getting a probability this is a dog. This process is not used for inference. This process is used for training. And so what we do is we take our training data and instead of the inference, which goes from data points to probabilities, we take these training points that are labeled and we say, what parameters would be most likely to explain this data? So if I had one data point at 20, and you said, what's the maximum likelihood, normal distribution, it would be one with mean at 20. Okay, it's only one data point, so I can't say what the standard deviation would be. If you had two data points, let's say at 20 and 30, I believe the maximum likelihood would tell you that the mean would be halfway in between, it'd be 25. And I don't know what the standard deviation is. My math's not good enough, but you can imagine it would be something, like a standard deviation of 5 or something like that. Okay, and so then you can imagine generalizing this to the more and more data points you have. It's not necessarily something that you can solve for because it could be over constrained. If I give you 1,000 data points and I say they all fall on one bell curve, which bell curve of all the possible means and standard deviations would give you, would this sample have the highest likelihood of actually popping out? Okay, and so Gaussian mixture models, this is just a generalization of it, where in this case, when you set K, we're going to say we're going to have K of these Gaussian distributions, and we're going to add them together. We're going to mix together points from, let's say case 3, points from distribution 1, points from distribution 2, points from distribution 3, and we're going to get our training data as the result of that combination of the 3. But in this case, we don't actually have in our labels whether or not any given training data came from distribution 1, 2, or 3. That's what the Gaussian mixture model has to sort of infer. And so this is a problem that has lots and lots of different possibilities. And you cannot directly, it's not easy to directly solve for what should the 3 means and standard deviations be. So instead, the expectation maximization does a thing where it does a random initialization, and you can think of it like k-means, you can think a little bit like gradient descent, where it just keeps nudging things a little bit until it converges. So if anyone has anything to add, please do, but that's my super high level overview of EM.
I have a question. So for like EM, it can go through like multiple steps of like making the model like fit better to like a given whatever your set of like instances in your data set,
Sure.
right?
Sure.
So I guess why does it take more than one step of like expectation and then like maximization to why doesn't it just immediately find the optimal fit?
So so you're familiar with gradient descent, right?
Yes.
So this is really just an algorithm very similar to gradient descent. If you start with initial random variables, you can tell whether you should nudge each one up or down, but you don't necessarily really know how much to nudge them up or down. So what you do is you take a small step and then you see if you still need to keep going or if maybe you went too far and you should go back the other direction.
So like when you start with like the initial maximization or your initialization, and then you go through like the whatever the expectation step, and then you maximize, it's possible, it's pretty likely that given your initialization, that it is impossible to find the optimal solution like after maximizing like whatever, like after the maximization step where you like find like the parameters that maximize the likelihood at like that the first step. Is that it?
Right. Yeah. I mean, you I think if you define the problem to be particularly simple and you had like certain distributions that like were really easy to, I don't know, to integrate or whatever, like you might be able to come up with a toy problem where you can nail the maximization in one step. But in the general case, you can do it for any function of any shape. It doesn't even have to be Gaussian. You can have any distribution and it'll still work if you do the iterative algorithm, because it's not asking you to, I don't know, I'm blanking on the word, but it's not asking you to have an equation that you just simply derive, here's the solution. Right. It's not just a closed form solution. It's just simply taking a step in the right direction.
Right. So like the maximization step in, I guess, like without like a super simple problem is not like you just like solve for like the maximal like likelihood and then you're good. It's like more like a heuristic where it's like you're just taking a step in the direction of the optimal solution and that's it.
Well, I mean, let's just imagine a three Gaussian distributions mixed in 2 dimensions, right? So this looks like those ellipsoids on a piece of paper, okay? So there's 3 means, 3 standard deviations, and in the general problem, 9 entries in the 3x3 covariance matrix. So we've got 15 parameters we're solving for. And if I give you random initializations on those 15 numbers, how confident are you that you could like go zoom to the exact perfect maximum in one step?
Right. I guess I'm not like, I guess I don't have like well, maybe I have like an intuition, but I don't really know like what it's doing, like how it's getting to like the solution, like each step, like, oh, it's taking a step towards optimal solution, but like,
I think it might have more to do with where it starts, right? Because a lot of times it doesn't know where to start. And so if it's, and correct me if I'm wrong, it's just my idea right now. So, much like what we saw in k-means, where it just doesn't know where to start. It's just kind of picking something out, right? So if you start from anywhere you want and you expect to get somewhere, you're going to get somewhere. It's just what that somewhere is may not be exactly what you expect or what you want, right? So it's oh, Ted's got some.
I took over. I'm sharing my screen here.
That's all right.
So let's say you have some training data and here's a very poor man's histogram of this training data. Okay. Oh boy, my lines are getting even more crooked as I go. And let's just say for giggles, I've got a couple weird ones here. Okay. So this is the histogram of my training data. And I said, it's 1-dimensional data. And I said, we're going to train a Gaussian mixture of 2 Gaussians. Well, I mean, like you and I can look at it by eye and it's kind of like, yeah, I'm pretty sure I know what this thing's going to look like. All right. Now, how do can I change colors? I've never used the whiteboard in Zoom before.
Couldn't you take the mean of, like, say if you've got 3 distributions, couldn't you take the mean of the standard deviations and use that as a reasonable first step?
Well, but the thing is, so humans are great inference machines, okay? So you're given one training set. These are not labeled as left and right. You're just given one training set. So So you have sort of an infinite, well, not an infinite, but you have a whole zillion different numbers of means and standard deviations you could do by splitting in different places, okay? So yeah, if I split it here and I did the mean and standard deviation of everything to the left and the right of this split, I would get a really good approximation. But if I happen to pick this as the point to divide left and right, so in this very simple case of just 2, where we just have left and right, it's only one dimensional, like our eyes can pick it out. But what I wanted to say, and I didn't realize I don't have different colors, but let's just say that your current guess is a bell curve that looks like, oh, whoa, it's a rectangle. I don't know what's going on. How come I'm not drawing anymore?
Is there like under like draw? I think one of the options is like a square and another is just like a line.
I'm my menu is, gotcha. Sorry guys. No, I don't know where my, oh, there it is. Sorry guys. All right. I think this is gonna work. So let's say my current guess looks like this. I'm off by a little bit. Okay. And I've got another guess, and they can overlap, and it's off by a little bit. So EM in its next step, it's gonna kind of push this mean to the left because it'll fit better. And it'll push this mean to the right. But if our original guess had 2 of them that were way over here, right? Like, you know, right? If our original guess was 2 Gaussians like this and like this, that are both way to the left of all the data, then it'd be very hard in one step to say exactly how much that, you know, they both need to move to the right, but exactly how much should each of these move to the right, and then how wide should they get?
I mean, I guess I'm like a bit like confusing what exactly like the maximization step is doing, because like you can like visually see what you'd imagine to be like a good fit, like for like these 2 like Gaussians for this like data set, but like when you go through one iteration of like EM, like something is being maximized, right? But it's like being maximized and it's not reaching the optimal solution. So I guess I'm like confused on like how that's possible.
Yeah, so at iteration I, if the blue is our current guess, okay, then what we would do is we would calculate the likelihood that all these black training points came from these 2 blue distributions.
Right.
Okay. And then what we would do, and this part, honestly, I'm not that sure, is we then need to say, which way would we nudge our parameters, our means and standard deviations, to get a higher likelihood value than the one we currently have?
Yeah, I mean, I think I get that like intuitively. It's like, yeah, yeah, but like maybe it's just a bit too like mathy to get into like the.
Yeah, so this is like the left-right nudging, right? And you can imagine that at some point then you wind up with a distribution that's got the perfect mean, but the standard deviations are wrong, right? So now the means might not change in the next step, but this standard deviation needs to get larger because a lot of this data is farther away from the mean than you would expect, right? You would expect 65% of the points are going to fall within 1 standard deviation, and 95 within 2, and 99 within 3, right? And on this one, you get actually too many points. You say, oh, wait a second, why does 85% of all my training data fall within 1 standard deviation of this mean, right? Too many. So for this one, I'm going to lower my standard deviation. For this one, I'm going to increase my standard deviation. And then by I think most of us can say intuitively like what the final answer will be, that a mean that sort of, has the mean here, but, kind of follows the shape of this histogram that's going to be the solution to this. Just to be clear, though, this one was easy for us to do. What's not so easy is if you have, I don't know what color to pick. If you have overlapping distributions. So if I said, here's the distribution of my data, you know, I kind of know where the means are, but I don't necessarily know what the standard deviations of each of those three should be and what the weighting of those three should be. So actually, I left out there's additional parameters, because in addition to this, you have a constant that each of these distributions. So you have a mean, a standard deviation, a covariance matrix, and a weight associated with each of the distributions. So you could say 5% of the population belongs to this distribution 1, and 95% belongs to distribution 2. So there's a lot of parameters.
But you're gonna have a calculable likelihood of a particular data point falling in a particular distribution. You won't know for certain which distribution it falls in, but you'll have some idea, and it could have equal likelihood of falling in one or another. Like, let's say you have 3 distributions, right?
So the problem, I think, I don't know if I'm explaining this well, I think the thing that makes this sort of intractable is that if I pick a data point that's here in this part of the histogram, okay, by my eye, I would say, oh, it's probably part of this distribution. But the reality is it could just be a faraway point that's part of this distribution. And in the real world, this happens a lot. So even though you have this clump of things here, there may be 1 or 2 points here that belong to this distribution. They're just in the tail, and vice versa. So when you have multi-dimensional distributions that overlap, you know. So guess what I'm saying is the splitting of this data into left and right halves would give you a close answer, but I don't believe it would actually give you the correct answer, because you're not taking into account that the tail of the right distribution covers in here, and there's a very small chance. So you'll be very close for 2 somewhat non-overlapping looking bunches of data, but you won't be exactly right, because you should be taking into account that there's a 0.1% chance that this data point actually belongs to this distribution. It's just out here. So it's a very complex, intractable optimization problem to just directly, solve by formula. Does that make sense?
Works for me. I don't know about anybody else, but no, I think, Ted, your example that you drew was too clean, if you will. If you would have had one that would have had half of them kind of intermixed or something like that, I think that's where the problem gets to be, because you can't kind of eyeball it. This one you can sort of eyeball, and as you point out, we're very good at intuition about somewhat good at intuition as humans, of seeing kind of there's division here. Oh, this is one pile of data and this is one pile of data. Therefore, they should, if you're going to say it's a normal distribution, this should split. But if you have it mixed up, because even in the example they gave in the book, you're dealing with, I don't know how many, potentially numerous dimensions. And we as humans, 2 dimensions is kind of the limit of our, it's Zoom's fault, Ted. If they would have given you a 8-dimensional space for you to draw this in, we would be much better off. But no, we don't do well at beyond 2 dimensions. So I think that's to some degree why maybe it looks like, oh, you could just directly get there, but you get to 7, 8, 9 n dimensions in space, and intuitively that gets very difficult.
Well, and I think I want to add something about this idea of intuition, because now I'm starting to feel like I'm making an assumption, right? because you have this data and the way it looks and the way Ted described it is, oh yeah, that's very clearly two different clusters, but all of a sudden I'm starting to see three now, just
Yeah, there could be a little third one here.
Yep. Exactly. And so, and then it goes into, what a human sees versus what a computer sees. And a computer is not looking at things like this. It's just kind of looking at numbers and doing all these calculations and then spitting something out. And that's where all those additional iterations come in, is because this is just what I found from looking at it when I started over here in the left-hand side. So now I got to move over here and here's a new set of calculations. You tell me which one is the better result.
For a human, if you made one of those dimensions, time, that this thing's going to vary over time, then I think it comes to an understanding that becomes, as Ted said, an intractable problem when you go to higher dimensions.
And that's where we are all the time.
Yes, exactly.
And we're very, very seldom just here in this sort of flat kind of scene. And
yeah, or like marketing, our market projections do it once and done, right? But it doesn't. It changes daily, seasonally, hourly, fraud prediction, things like that. So.
All right, I'm going to turn things back to you, Kalika.
All right. Do I have to hit the button again? I think I do.
Yes, I just completely took your share away. Sorry.
That's all right. We got a lot of information and talking done. Then that's kind of the point. That makes it fun. So my only question that I've got left is, why would you set the default to 1 when you know you've got to go more than one time? But that's something to kind of just remember and look out for when you're working with Gaussian mixture models. So next up, I just called these two funny pictures. Those are the pictures you can see if you have the actual paper book. I don't know what the online book looks like, but if you have this one, those are the ones on 261, 271, and I just called them computational complexity. And these diagrams just go over Bayesian Gaussian and regular Gaussian, and like, okay, this is the level of complexity for computing these things. We find out there's a covariance type hyperparameter that will increase the chances of finding your optimal solution. Your default is set to full, which means that any cluster can take on any size or shape. And that's where this sort of idea of, you want to play with this one a little bit comes from, because if you have that set to full, you're going to end up with just this kind of mess of ideas there. Your covariance hyperparameter also impacts your computation speeds. Tight and full will take the longest amount of time, and the spherical and diagonal ones are a bit faster. Anybody have anything they want to add to that one? We only got 4 slides, guys, so drop in, please.
So I would like just to add that mathematicians, when they have a chance, always choose the simplest thing. They choose 0, they choose 1, and when they need to start with something, this is what they usually do. And about points, actually, normal distribution is not limited to anything. It goes from -infinity to infinity. It is just on the picture, we don't see it because it lies very, very close to horizontal axis. But in reality, when you use normal distribution, your numbers could be anywhere, your points could be anywhere. It is just the probability of them being too far is very low.
Okay. What you got going on there, Robert?
No, I mean, I was just thinking like if there was any way of like any intuition behind picking any of these like covariance hyperparameters outside of just, I mean, all I can think of is just visualizing the data, like seeing what it, but like even then it's, I don't know how you would do that for like in like higher dimensions, or if this is just something you just start with these like, I don't know, the faster ones because it's just, you know, simpler to compute or faster before moving to the, you know, like the full search, or yeah, if there's any like other way of doing it.
My 2 cents is with most of these things is you, it's an experience, you know, it's an experience type thing as you use these models, and you then just have to look at the data and say, oh, well, you know, based on my experience, I would set, you know, this parameter to 5 or whatever. But yeah, I don't have anything off the top of my head more to offer on that. But that's just how it is. I do most of my work in neural networks and neural network models, and that same question comes up there too. And it's even worse because you can change, you know, model architecture, plus you can change all these other parameters at various steps along the way to the solution. And you know, we have this kind of like joking thing. Well, the way you do that is a grid search, where a grid says, here's all your parameters, and you know, just adjust one at a time, and then, you know, adjust them in pairs and things like that. But there are tools like AutoML tools that will take a look at the data distribution and make some guesses. But those are trained more on what the AutoML tool has seen from various data distributions. It's a learned thing, not a priori. You know, you can start at a certain set of values, and Bob's your uncle, as they say in the UK. You know, it's tends to not be that way. At least it's been in my experience.
Yeah, Robert, I'm looking at page 265. So, you know, if you say diagonal covariance matrix, you know, he says that the ellipsoids are going to be parallel to, you know, the axes. But actually, I think there's a much simpler way of saying that. If you say diag, that means that all of your variables are independent. So the way that variable x1 varies is going to be a normal distribution, but it's completely independent of the way that x2 varies, and completely independent of the way that x3 varies. So if you think your features are distinct and independent, then you could choose diagonal. If you just have a whole mess of features, and so you have, you know, you're doing something with whatever housing prices, and I don't even know if that's a realistic example, but you know, you've got number of rooms, you know, size of rooms, square footage, number of bathrooms. I'm sure a lot of those things go hand in hand. The bigger the house, the more the bathrooms, the more the bedrooms, the bigger the bedrooms are. You know, those things, I'm not saying it's 100% perfect, but they are definitely correlated. They're not just completely random, independent of each other. So then that might not be a great assumption, you know, for that kind of data. If you choose spherical, then you're basically doing something very similar to k-means. So it means that it's going to have the same standard deviation for all of your variables, which is what k-means is doing. Which is why for k-means, what we talked about is you have to scale the data, or if you don't scale it, you have a you know, the distance in the y direction, if it's, you know, if the variance is twice as much, then you're weighting that y dimension, you know, more than the x dimension, or x2 versus x1, whatever. So same thing here. So spherical is saying, you know, I'm gonna treat this distribution as having the same variance in all directions.
And so this raises a question, and my question would be, why not just, if it's a spherical distribution, outside of maybe wanting that probabilistic ability, that sort of soft clustering that's built into the model, why wouldn't you just use k-means?
This is a good question. I don't know if I have the perfect answer. I would say it depends on the problem you're solving. If you're trying to solve anomaly detection, then inherently you want that probabilistic model. The other thing is that we mentioned last week, certain clustering algorithms require every point to be in a cluster. Probabilistic models can have low probability, so although technically speaking, it's, you know, applying them, but the shape of the cluster is not as influenced by outliers. And so you may actually get better clusters, so to speak. In this case, it's Gaussians, right? You may get better ones with this model if you think your data is very noisy and has lots of outliers. I think in the book, he might have mentioned something about there's a difference between novelty detection and anomaly detection. So if you think you have no outliers in your data, then you could, you know, just do something where you train it and you expect everything. But if you know that you already have outliers in your data, then it's possible that a spherical Gaussian mixture will actually give you a slightly better model than k-means because it is discounting those outliers.
You know, in particular, in addition, when you work with this kind of distribution, you want your points to be concentrated around some area. And sometimes they're not just concentrating, sometimes they're spread out. And you just want this spread out thing to be divided on the things which are very spread out, which have actual distances between them. It is just, I recently worked with such kind of problem. And I was, you know, what I was doing, I was looking at times when Russian trolls would post their tweets on Twitter. And they all are, you know, I don't know if the Twitter, if the people who harvest the data did it, but they all differ by at least 1 minute. So they're not actually too much, very concentrated in one point. Nevertheless, I used actually GB scan. I discovered that there are clusters of posters which has more than what I wanted. Just a minute, I'll look it up. Okay, in 1 hour, the poster, the account had more than 31, at least 31 posters. And the length of this cluster was 62 hours, 66 hours. So apparently it wasn't done by one person, or it was probably even automated, which is very good information for me. In this particular case, the Gaussian mixture mode may not work well because they're more or less spaced evenly.
Okay, thanks,
Okay.
Maya. Yeah. So going back to your question, the last one, tied, I don't know if I tried to come up with an example in my head. Let's say you had, you're doing something where you're looking at some disease and you treat men and women differently. Maybe tied would be something you would try because you would expect that the disease would have sort of similar correlations with your blood pressure, similar correlations with diabetes, similar correlations with whatever, you know, BMI, but just that you will have a different center for men and a different center for women. And so then by saying that the mixtures are likely to be similar shape, but just have different centers, then that might be a reasonable situation to try tied.
Great. Yeah, I mean, it's mostly like you would have to like intuit what like the data looks like, right?
Yeah.
Because I don't know if there's
Right, but I'm just
Yeah,
saying,
you
like,
can't-
you wouldn't
yeah.
expect weight and blood pressure to be completely independent in men, but correlated in women. That seems like an odd thing, right? So if you had very similar
Mhm.
correlations, then basically that's what Tide is saying, is that you have similar covariance matrices between men and women.
Right. Okay.
Yeah, I've always had to just try them all. I've seen some pretty interesting things because when I was doing boot camp a while back, over a year ago actually, we were originally told to kind of look at run some statistical models and try to get a feel for things, and then you start to try to get this feel, and then all of a sudden what you think should be what you think should be the optimal result based on these statistics that you ran turned out to be the complete opposite when it came to working with the data. You learned something completely new and found out that you might have totally missed out on this incredible model if you had skipped it because you went with this sort of trying to find what you want, but just based on statistics or whatever it is you think. I think it should be tied because of the data looks like this, and then you skip the full option, and it turned out it should have been full, kind of deal, unfortunately. Has anybody had anything where it's just like not like that ever? Okay. So we also learned that Gaussian model mixtures are good for anomaly detection, so that you can find those things that deviate out of the norm. You do this by looking at the density of the clusters, which is returned as a score of the samples, and the anomalies are those clusters that are below an agreed upon threshold, which is going to be that agreed upon threshold seemed to sort of coincide with, I would say, what your domain you're in. So where you're working at or what you're looking at, there's usually some kind of idea about what this threshold meets and and whether or not you want to use that threshold to, determine where the anomalies lie. Now I had a question, which is kind of a silly one now that I've talked to you guys, and it was, okay, so we're looking at a normalized data set. And let's see, hold on. So in cases where an extreme number of outliers are present, they recommended an elliptic envelope class as a more robust form of anomaly detection. And I was wondering if, is that the only thing an elliptic envelope might be good for? And has anybody used it? And what do you want to talk about regarding that point?
I haven't used elliptic envelope. I'm not familiar with it. Ryan, I don't know if you've lost your voice, but I don't know if you can type anything if you've ever used it. All right. He hasn't either.
Anybody have any like really fun stories on anomaly detection or novelty detection for that matter, which is like anomaly detection, but does something else? I forgot what it was.
I don't know if you have a slide. I think one of the things we can talk about in the last 15 minutes is there are non-parametric methods. And so I think people here have likely tried out, whether on a toy project or on a real world project, some of these other outlier detection algorithms. So they are not statistically based, but they often work well.
So I think
You-
PCA was mentioned kind of sort of at the end as an anomaly detection model, as you being used for anomaly detection.
Yeah,
And I-
somebody can tell me if they've ever used it, but I tend not to. Actually, I just showed that thing the other week about a way you do PCA on time series, and you can actually detect anomalies. But generally speaking, you know, if you consider the reconstruction error for PCA to be your signal telling you whether or not something's an anomaly, I don't find that tends to be a great model.
So I've used PCA with a new technique called RIDIX, and it's like a predicts technique for detecting risk in terms of fraud detection. So it's this technique, I haven't found in any books, but it was part of a research article. I did it once in grad school. And the idea is that when you're dealing with fraud related data, it's very different in a sense where you can't always rely on machine learning models when it's fraud detection. And so you have to go with an unstructured technique. And the reason why is because oftentimes one fraud related incident is going to be totally different from another. Especially if it's organized fraud. And so with this technique, God, you make me like go through, I'm trying to look through like my old like project to see if I can pull up more about it. But in a nutshell, it was a technique of using PCA aligned with this RIDIX technique, which was an unstructured statistical technique, and you used it to detect potential fraud. And you couldn't use a supervised machine learning model because you can't really use that within fraud because each fraudulent case or issue is going to be different. So, you know, an organization may not have an abundance of data to predict the likelihood of fraud with a supervised model. So I had to use that for an unsupervised task. And I only did it once, but I do know that it is used heavily for that because you can't use a supervised model.
Ted, I think you're muted.
Sorry, too many windows. Finally found the mute button. How is that spelled? The name of that algorithm?
It's predicts. It's like PRIDETS. I'm trying to
Okay.
go back through like my old school like grad courses to figure out which one it was, because there was a whole entire like research article that was about the technique and how you would use that for fraud, and it pick out the outliers for you.
Yeah, no, I was just trying to see if I could find an article about it or something. All right, well, while I'm doing this, thanks for sharing that. What about, are there people who've used isolation forests, local outlier factor? Can anybody share about that? Gosh, I'm not seeing it, Christy. Is it PREDITS?
Oh no, PRIDITS. I'm going 1 second. If I don't give it to you in this session, then the next session. I'm like going through like all my old school homework files. I'll find it for you.
Oh, Kirk's got a link he just posted.
Oh, here we are. Is this on is my screen showing? Predit is a useful technique.
Yep, that's it.
Really cool.
Interesting. Okay. So I'm trying to remember, what does Aurélien say about isolation forests?
Let's see.
Yeah. So the idea is, you know, if you build a random forest on your data, then generally speaking, you know, it uses trees So you have splits. And so the sooner something on average gets split out into a leaf, the more novel it is. And if some of your data takes every single tree, it always takes until the very last split, then that means that it's pretty much right, heavily mixed in with a lot of very similar looking training examples. So it's very hard to split it from its sort of nearest neighbors. I'm using that term somewhat loosely. So you can basically write, if you build 1,000 trees in your forest, a data point that has a score that says it gets split super easily is more likely to be an outlier than a data point where it has to go very far down into the tree in order to, on average, in order to split it out and make a prediction. So that's the high level gist. Does that make sense for everybody? Does anybody else have anything to add for that?
There was at one time a Kaggle competition on credit card fraud. Does everybody kind of remember, or people remember that? And I was curious to know what models ended up doing the best on that. It's been a while since I've looked at that.
That's a good question.
Yeah. Let's see, looks like somebody's using SVM. And where's the ranking here? Let's see here. I think they got like 97%. It says they're using SVM.
Is that a labeled data set?
Yes, it is. It's kind of funny if I remember the data set correctly. It has things you would expect, like I think time of day, amount, things like that. But then they've done some sort of, to hide the fact whose data it is and what exactly they used. They did a PCA and created like 20 other columns from maybe, I don't want to, I'm just pulling these out of the air, but maybe out of 100 different values. They did kind of a PCA thing, and that's what they gave you in the data set that you had. So you had like a few columns, that made sense, time of day, amount, blah, blah, blah. And then you had all these, just these numbers essentially, feature 1, feature 2, feature 3, feature 4. And then you had, that's the data you had to work with. So it is what it is, but it's in Kaggle, and there is a credit card.
Yeah, the credit card fraud competition I'm looking at is 4 years ago.
Yeah, it's an older one. It's an older one, but it was a lot of times the unsupervised models didn't do as well as I would have thought. Just my intuition on that. Some things like some older methodologies seem to work well. Let's see here. But anyway,
Well,
I always found that an interesting one to look at. Sarah.
Yeah, I mean, generally speaking, if you're doing like anomaly detection, you're not going to be able to use the supervised learning technique, because that assumes that you have training examples and that the new cases will look like the old cases. So if fraudsters are going to evolve and do things differently, if you're looking for, machine failures, assuming that you don't just have this handful of ways that machines fail, but they can fail in all sorts of different ways, then you can't really use supervised learning. Because I noticed like there's some people who talk about like logistic regression or whatever. And again, that's only going to work if you have examples of what you're trying to detect.
And I think one of the things Aurélien mentioned, and I'm pretty sure it was here, was that he was using anomaly detection for data cleaning, actually, for cleaning up, getting the outliers out of your data, and so that you can actually then go off and use it as your for your data modeling needs, since outliers are such a burden on our predictive models. So
I have not ever done that. I don't know if any of you guys have done that. I mean, I definitely have bad data. I have noisy data, but I've never tried using outlier detection to try and clean up my data.
I tend to zoom in on those outliers and figure out exactly what's going on with them, and you know, those are the ones I'm spotting and cleaning up individually. So
Yeah, exactly. When you're doing your EDA, if you have, you know, temperature of the room and you've got a value that's 1,000 degrees, you know, like
I've got a
without,
broken sensor to fix.
but yeah,
right?
without even having a model, you know, we would probably say, that doesn't look right.
The bigger question is, what do you do with that temperature then? Do you drop the row, or do you, put the mean in, or?
Call up the customer. Hey, how hot is it in there right now?
Yeah.
What was it
your data set is
actually?
probably from your data set is probably from last year. You know, on the 3rd of January last year, what was the temperature?
I
That's
could
not
use
going
you
to
to
work.
check your electric bill for me.
Well, what's that saying? That 60 to 70% of machine learning is fixing data, right? It's not running the models. It's fixing and pre-processing data.
Right. But yeah, so
I don't think we have formal discussion of like imputation in this book. I have not, in my work, had to do very much of that. So fortunately for me, when I see bad data, I usually can just delete it.
You must have big data sets, Ted.
Yeah. We were going to do something like 30 million phone calls this year. So if I see, 100 rows that have some wacky value, I just delete them out of my training set.
Yeah. You're fortunate.
Yes. Then I read these papers where they did like some medical experiment and the N is 40.
Yeah, that's a space I came out of, working for drug companies and things like that. You're right. Especially I was in the oncology division, and so some cases we don't have a lot of samples and things like that, and unfortunately we can't go back and and retrieve after the fact. We can't rerun the experiment, so it's just not possible.
Yeah, but man, you're squinting really hard at those 40 data points.
Well, and I will say, I've been on teams where we spent, we got led down the merry path, right, because of those 40 data points. That wasn't the data, right? So, and then anyway, yeah, it's a real problem. So another thing I saw for anomaly detection, and I don't know if anybody else has heard this, is using training a GAN, since that's unsupervised. We're getting kind of ahead here in the book, but an unsupervised way of, creating, essentially treating something to create realistic data. And then once you had that for that domain, then you ran your data through it, and it would say, that's infeasible, if you will, to be valid data for that. So.
Yeah, we haven't talked about, but your GAN has a discriminator.
Right.
So it is saying whether it thinks this data is in distribution or out.
Right. So, well, it learns how to do that, right?
Right, but I'm saying once you're fully trained, you've got this discriminator that you give it an example and it'll say whether or not it thinks it's in distribution or not.
Right, so that was one of the interesting things I saw, and a new way to do anomaly detection was to use a GAN. I hadn't seen that used before, but if you think about it, just conceptually, it sort of makes sense.
Yeah, I like it. That's a very non-statistical, non-parametric method. I've noticed that Kaggle on their toy competitions has more and more shied away from using real data sets, and instead they're using GANs to generate synthetic data sets. It allows them to generate more data. So like if you're doing a thing where you're predicting the Titanic, there's only X many passengers. But what they can do is they can say, I'll give you a data set of 10,000, of 50,000 passengers. And so then you have richer data to try to detect patterns. And so it frees them from that. And it also frees them from just, screwy bad data. If you look at the Boston housing data and there's this weird house that went for way more than it should have, like that's going to screw up when you're, building these models.
Yeah.
I mean, it feels to me like using synthetic data is very valuable for testing certain kinds of model evaluation algorithms. But when you're talking about testing the practical applicability of a particular modeling analytics approach, it feels like if you're synthesizing the data, you're like putting the ball on the 20-yard line and saying, oh, well, if we don't get that home run, we don't get the touchdown, we'll kick the field goal. It just doesn't feel right in terms of solving the hard problems of
That's actually
analysis.
Yeah, I would say that's why GANs are becoming such a big high usage, because GANs, the goal in a fully trained GAN is, as Ted mentioned, there's this discriminator component, but the goal is that you can't tell actual from generated data in that scenario. That the distribution of what real people do and things like that, you've modeled it well enough that somebody looking at it can't say, is that a real person or is that a fake person?
Well, but it isn't the counter to that to say that no one's figured out how to distinguish the synthetic from the real data. That doesn't mean that there isn't a way to do it.
Yeah, but it's a very much harder problem. And it happened. The GANs had the advantage of their original thing was pictorial data. I mean, like people pictures and things like that, of making those to the level, those deep fakes that you see out there are essentially an application of a GAN. So, they're good enough to make people look like they're saying things that they never did. And if you can validate that data, create that in a data set, you've got something maybe. Anyway, that's my GAN thing.
No, it's an interesting, it gives rise to a new interesting set of questions about how you gauge whether or not data is real world or in fact machine generated.
Yeah, and the usage and training is really useful. Ted knows this. At Tesla, they are building their autopilot system, and so they needed to have they needed to teach the system what to do in very unique scenarios, and one of them was people running down the road or something like that, which down in San Diego, I know Ted and you and I have talked about this before. They do have actually signs there because they have people coming across the highway down there and things like that, and that is actually in the Tesla autopilot data set, a case. Now, obviously they could drive 1 million miles and not capture that, but they can synthetically add that to their data set, or did synthetically add it to their data set using a GAN. So
yeah, and I am sympathetic to the argument that we don't really know whether their synthetic data was good enough. So when you really have a person, when you have a little kid that loses their ball and they run out into the street, is that synthetic good enough that the car will say, oh, this is the same thing as what I've seen before? So kind of to Richard's point, I am sympathetic. Like we don't know. We hope. And it is useful to have synthetic data so that you can have all these situations,
right.
Driving in the middle of, a hailstorm with, tennis ball sized hail. You don't necessarily, want to go chasing, hailstorms and drive your Tesla into it just to capture training data.
Yeah.
One of my favorite examples of GANs is actually involves what they were doing with Rosie at is it the MSOE, Milwaukee School of Engineering, where they're and this is I think a presentation I attended months ago, probably about a year ago or so, but they're using GANs to generate like cancer cells. or was it either cancer cells or kidney disease or something like of that nature, where they didn't have enough of these specific, cancerous cells, so they generated them so that they could actually get better detection on them. And I found that very exciting, actually, because it's something we definitely need.
Yeah, when I was the company I worked at, we were always looking to do that. Now, I haven't been there in a decade, so we didn't, at that time didn't have the capability. But when I look at a GAN and think, man, what if we could have done that? That would be really sort of neat. So.
Okay, and I should emphasize, though, in the situation that they were they actually, instead of just like letting the computer do everything, they generated these synthetic situations and then handed them off to doctors and let the doctors label them, individually to make sure that what they were using would actually come in and generate naturally. So
yeah, that we had several pathologists on staff just for that. We thin section tumors, not to be too gross, but have them tell us what was important, and then the data and team that I was part of would have to go look through and say, well, what do we think we can find in such a thin section slice and detect in a tumor and things. So that was our job, but GANs would do a better job. If anybody's interested, there's this site, thesepeopledonotexist.com, I believe it is. And if you look at that, every time you refresh the page, you'll get another picture of a generated person. And you can think of, if they can do a human face, that's a fairly complex object that we can actually generate data. So anyway, just taking us way off track, but just for fun, it's always fun to watch. And when we get to GANs, we can come back to this. There's another tool called GauGAN from NVIDIA that has a cool little drawing package. So anyway.
Yeah. Yes, so the good news is we are going to talk about GANs in this book. They are covered, not in the level of detail at the time that this book was published. A lot of the stuff we're talking about is newer than that, but we are going to get to that. So we are past time. So to kind of wrap things up, we talked about a number of different things, and I do think if we could just take at least 30 seconds, 1 minute. So for your last slide, Kalika, if we're going to be principled, if we say we do have some concerns about when to use and what are the right hyperparameters and this and that, we need some way to measure the goodness of our mixture models. And so the author does actually talk about two ways in which we can evaluate, well, how well does this mixture model fit the training data that we shoved into it, right? So if you wouldn't mind just wrapping up with your last slide, and then we'll call it a day.
Yep, quick and easy. There, of course, words I can't pronounce against. Alkaike and Bayesian information criterion that you can use. Supposedly, the lower the score, the better the choice. And if you are looking for a better model, you can also just do like a grid search, as we mentioned earlier, on covariance type. And last but not least, Bayesian Gaussian model mixtures also exist. But if you use one of them, you're restricted to ellipsoidal shapes. And that would be it.
Yes, and so I've been doing a bunch of reading. So the Bayesian mixture models uses a technique called variational inference, VI. And I've been trying to read about variational inference. The math/statistics is a little bit hard for me to get through. But if any of you are interested in this topic, it seems like a lot of the research right now in machine learning is trying to apply things like variational inference on top of some of the other things that we do today. And then you'll also see diffusion models. So I would say those are two of the things, but VI is related to Gaussian mixture models. And the author Aurélien does touch on it in this chapter, where you can see that it sort of is this hard problem, and somebody has cleverly figured out how to turn this somewhat intractable integral into a maximization problem. And so they are able to create pretty good latents in order to generate these distributions. And in this case, you know, it'd be fairly straightforward, where you just have a latent that's kind of telling you how many clusters do you have in the first place. So like Kalika, you were saying, could I squint and say maybe it's 3 clusters, with the third cluster being fairly low, you know, membership, or is it just 2 clusters? I don't know. And so this is the kind of thing that you can use variational inference for.
Cool. Yep. And that's it.
All right. Thanks, Kalika. Thanks for being our discussion leader for 2 weeks in a row. As I said at the top, I think everyone was here. I don't know that anybody joined in the middle, but so no book club next week or the week after. Jerry is going to kick off part 2 on January 8th in 3 weeks. And then after that, it's going to be all TensorFlow, all Keras from here on out. So it's almost sort of like really 2, you know, separate kind of books. This is the Scikit-Learn book that we're finishing up now. And next comes the Keras TensorFlow book, so to speak.
Thank you, everybody.
Yeah, thanks.
Bye, guys.